Okay, so we've talked about degrees and how to measure angles in degrees. Now we're going to talk about another unit of angle measure called the radian. Now, the radian is defined as being the measure of the central arc of a circle that intercepts an arc equal in length to the radius of the circle. That's easier seen than said, okay? Basically, it means if you've got a circle, we know that this is the radius, right? The radius is anywhere from the center to, any point on the circle's edge there, right? Well, when this arc right here has a length of r, which is the same as the radius, this angle right here has a measure of 1 radian. Okay? So that's what 1 radian is. Now, we know the circumference of a circle is given by the formula 2 pi r. The arc length formula, so the length of an arc, is S equals r times theta, right? Where r is the radius and theta is that central angle here. Now, theta is just a Greek letter. We tend to use Greek letters to represent angles. So, just solving this for theta, we get that theta is S over r. Okay? That means this central angle can be found by taking the arc length divided by the radius. Well, in a full circumference of 2 pi r, if that arc is a full circumference of 2 pi r, we get that 2 pi r divided by r is 2 pi. Basically, all this stuff is saying that 1 revolution, or 360 degrees, is the same as 2 pi radians. All right, so that's what all this stuff was deriving for you. Now, with that said, let's go back up here. We know from the previous part of this section that we have 0 degrees, 90, 180, 270, and then back here's 360 degrees. So, in radians, we have, our starting point here of 0 radians, and 360 is the same as 2 pi. So, let's start talking in terms of like halfway points. If 1 revolution around is 2 pi, then that stands to reason that halfway is half of that. So half of 2 pi is 1 pi. Okay? Then from 0 to pi, halfway is this 90 degrees. Half of 0 to pi, half of that is pi halves, or pi over 2. So we basically get that every 90 degree increment is the same as pi over 2 radians. So we have 0, pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. So you see how I did that in terms of unreduced fractions. Okay, so let's talk about how to convert between degrees and radians, because there's instances where we're going to need to use radians instead of degrees. Now, pi radians is the same as 180 degrees. Radians are what's called an invisible unit. Because of how they're derived from that arc length formula, they're what's called an invisible unit. So you can either write pi radians, or if you just write pi with no unit, it's assumed to be radians. So that means if you were writing, say, 2.5, that means 2.5 radians. If you mean degrees, you have to put that symbol. You have to put that unit on there. If you don't put that unit, it's assumed to be radians. So it's very important that you know that. All right, so if we're going to convert to degrees, we can do this by either by using a conversion factor, or there's a shortcut. I'm going to show you the conversion factor first. A conversion factor is basically something that you multiply by that is 1. It's something over itself. Okay, that's what a conversion factor is. And we know that in multiplying by 1, we don't change the value, we just make it look different. So, if you multiply say you have pi over 6 radians. If I multiply by 180 degrees over pi radians, the radian unit will cancel. Also, the pi's will cancel, and I'll get 180 degrees on top, 6 on the bottom, which then reduces to be 30 degrees. Another way of doing this is you can just replace pi with 180 degrees. So then the pi over 6, if I just take that pi right there and I replace it with 180 degrees, you can see I get 30 degrees. So if it's pi over 4, I replace the pi with 180, divide, get 45 degrees. 9 pi over 8, replace the pi with 180 degrees. You'd have to break out the calculator here, multiply that 9 times 180, and then divide by 8, and you get 202.5. I would encourage you to grab your calculators, pause the video, and do these computations with me just to make sure that you can get the same numbers that I'm getting. Okay, so all I'm doing is replacing pi with 180 degrees and then doing that computation on the calculator. Now, what happens if you don't have a pi in there? 5 radians is different than 5 pi. We can't use that shortcut, right? If you don't have a pi, there's nothing to replace. That's when you're going to have to use that conversion factor. The conversion factor we're always going to use is going to be this 180 degrees in pi radians. Notice how my units are stacked here so that they cancel. This radian divided by radian. So this becomes 5 times 180 degrees over pi. So we get 900 over pi degrees. If you want to simplify that into decimal form, that's 286.48 degrees. That looks really weird, okay? I know some people, that bothers a lot of students. And then they do something even crazier, right? They'll get to this point and say, oh, I got to replace that with 180. No, don't do that. You're already in degrees. So if you find that the replacing pi with 180 degrees is a little confusing, then you might want to just stick with the conversion factor. Now let's go in the other direction. Okay, so before, here we were converting radians to degrees. Now let's convert degrees to radians. Again, I'm going to use the conversion factor. So 60 degrees. But look, last time for the conversion factor, I had the 180 on top and the pi on the bottom. Here I've got pi on top, 180 on the bottom. So do you have to memorize when to use which? No, you don't. Just keep in mind that the order that you're going to put this in just needs to cancel those units. Right? So we need that degree and that degree to cancel. Just like up here, I needed the radians on the top to cancel that radian on the bottom. All right, so the degrees are gone. I get 60 times pi over 180. Now the 60 over 180, that can reduce. That reduces to be 1/3, which you can then write 1 pi over 3 or just pi over 3. You know, kind of like if you had x over 3, you know that coefficient's understood to be a 1. Same thing here. It's understood to be a 1 right there. Okay. We can do this with negative angles as well. Because it's degrees on top, I'm going to put this 180 degrees on the bottom, so those will cancel. This is my conversion factor. This stuff in blue here is 1 because it's something over itself. So we get negative 135 times pi over 180. You can use your calculator to reduce that. Okay, so just use your calculator. Don't put the pi in there because then you're just going to mess your calculator up. But just use this part, put it in your calculator, hit math, fraction, enter, boom. You'll get negative 3/4. And then just pi's along for the ride. Okay? Same thing with the 450. Use your calculator to reduce that. You'll get 5/2. Pi is along for the ride. Some students tell me that it's easier for them to convert from radians back to degrees. So they'll just throw 180 right here and then multiply that out, and divide by 2 and see if they get 450. You can totally do that if you want to. Okay, so we talked about arc length earlier. We have this arc length formula of S is equal to R theta. R is your radius of your circle. Remember, that's always measured from the center to any point on the circle. Okay? Theta is an angle that has to be measured in radians. That's really important. Okay, it cannot be in degrees. It has to be in radians. Another formula that we're going to use is a formula for linear velocity. Okay? Now, velocity in general is distance per unit time, like miles per hour. Right? That's what this is as well. It's a distance that happens to be our arc length distance divided by time. You can use any combination of these. You know, if you wanted to put r theta right here, you could, because this s is the same as this s. Now for linear velocity, we get units of stuff like feet per second, miles per hour, meters per minute. Those are the kind of units we're going to expect to see with linear velocity. I say that because the other velocity we can talk about is angular velocity. Angular velocity is measuring the angle covered per unit time, not just the distance per unit time. Okay? So linear velocity measures distance per unit time. Angular velocity is talking about what kind of angle is being covered. So angular velocity, think of it as like a circular velocity, you know, like a merry-go-round or a Ferris wheel or something like that, something going in a circle, or like the tire on your car. That's what we're talking about an angular velocity. The units for the angular velocity, because this is an angle, could be radians per hour. We could measure it in revolutions per second or degrees per minute. But notice all of these are units of angle measures. Okay? There's a relationship between the linear and the angular velocity. This looks like a W. It's actually a lowercase omega. So if you see it somewhere that's kind of written all scripty and weird, it's, you know, the Greek letter omega, but we're just going to call it W. Be a little easier there. There's a relationship between these two. Okay? So if you've got this linear velocity of s over t, and we know that arc length is r times theta. S is equal to r times theta. And we know that angular velocity is theta over t. We get the relationship that the linear velocity is r times the angular velocity. All these are on your formula sheet, so you don't have to memorize these. Okay? But I want you to see how these come about. I don't want you to think it's some kind of magic that's happening here. Okay, so on a carousel, the outer row of animals is 20 feet from the center. The inner row is 10 feet from the center. The carousel rotates at 2.5 revolutions per minute by the linear speed of the inner and outer rows in feet per second. That's going to be important, okay, that feet per second. So we're looking for the linear speed or linear velocity. Okay, speed and velocity are synonymous. So my linear formulas are s over t or rw. How do I know which one to use? Well, it gives me the 2.5 revolutions per minute. Because of that unit, I know that that is an angular velocity that I was just given. Okay? And I'm given the radius for the inner and the outer. I'm given both of those radii. So I'm going to use this formula. So I've got the radius and I've got the angular velocity. So here's what we're looking at here. We've got this carousel or merry-go-round. The outer animals here are 20 feet from the center. The inner animals are 10 feet from the center. So if we look at the outer row, we use this V equals RW. We have this radius, and then we have this angular velocity. Now it's not as easy as just multiplying this. Sometimes it is. But how do I know that I'm not just done after multiplying this? Well, because of the units. Feet per second. There's my feet, but I don't have per second. And I've got a revolution in here. So I've got to do two things. I've got to get rid of the revolutions, and I've got to change this minutes into seconds. So I'm going to use two conversion factors. That's these blue things. So the first one is 1 minute is 60 seconds. How did I know to put the 1 minute on the top and the 60 seconds on the bottom? How did I know not to put 60 seconds on top and 1 minute on bottom? Well, my units tell me. They're the ones whispering those sweet nothings into my ear, tell me what to do. So this minute cancels that minute, and I'm left with seconds on the bottom. You're going to get rid of the revolutions by changing those to radians, because radian is an invisible unit. We know 1 revolution is 2 pi radians. I put the revolution on the bottom of this fraction, of this conversion factor here, so that revolution would cancel that revolution. And I have that 2 pi radian, which, you don't even have to write that radian. It's invisible. So when I multiply all this out, I've got 20 times 2.5 times 1 times 2 pi. I just didn't write the 1 in there. Over 60 times 1. And my units are feet, gone, gone, invisible. Over, gone, seconds, gone. So the only units I have to write are feet over seconds, or feet per second. So grabbing out the calculator, doing 20 times 2.5 times 2 pi, don't forget pi, all over 60, I get 5.2 feet per second. That's the outer row, because I did the 20 feet. The inner row, I just have to go through and do the exact same thing, this time for 10. Or if you wanted to, make it a little bit easier, you could say, well, the radius is just half, right? 10 is just half of 20. So you can just take that and divide it by 2. So if you were thinking, I'd just divide that by 2, boom, got the answer, you would be thinking correctly. Make sense of your answers here, okay? 5.2 feet per second. Okay, that's not too far. I've seen students do this problem before, and they get something like 52 miles per hour. Okay, if you think a merry-go-round is going that fast, that's like the merry-go-round of death. Kids flying off, screaming for their mommies and stuff. Make sure that your answer seems reasonable, okay? Just keep that in mind. All right, last one. The minute hand of a clock is 3 inches long and moves from 12 o'clock to 2 o'clock. How far does the tip of the minute hand move? So let's draw a picture of what's happening here. So we've got a clock, which is circular here. This minute hand is going from 12 to 2. Now you'll see I've got little 3s right here. That's because the minute hand is 3 inches long. So you can think of that as the radius. Because the minute hand doesn't change size as it moves from 12 to 2. It's still, 3 inches long. This one right here is just, because of the clock, right? 12, 1, 2, 3, that kind of thing. That's the only reason that one's there. So how far does it move? Now, that's asking for the arc length, which is S is equal to R theta. So that's your arc length formula. R stands for the radius, which is 3. And theta, this angle right here, boop. Now I put it right there. It's actually this entire angle. I didn't want it to look like it was just that one angle. That thing right there. There's theta. So now we got to figure out what theta is, because we know what R is. So only thing we're missing is theta. So what angle is this? All right, well, let's think about this. On a clock, these segments are all equidistant. They're all the same distance away from each other. So we know that from 12 all the way back around to 12 is 360 degrees. So if I split that into 12 pieces, that means each segment is 30 degrees. So like going from 12 to 1, 30 degrees. 1 to 2, 30 degrees. 2 to 3, 30 degrees. See what I'm saying? So 2 segments would be 60 degrees. 60 degrees is the same as 2 pi over 6 or pi over 3 radians. So right here I just went ahead and changed 30 degrees to radians by using that conversion factor, where those degree units cancel, and I get 30 pi over 180. Now some of these angles you're going to see more than others. And you just might get used to seeing these. If you've had a trig class before, you may just already kind of know that 30 degrees is pi over 6. You know, or 60 degrees is pi over 3. Some of those just kind of stick with you. Okay, so now we've got our radius is 3, and we've got our angle that's 2 of these 30-degree segments, or 60 degrees, is pi over 3. So my arc length is just r times theta. And of course I don't have to write radians. It's an invisible unit. I'm just writing it for now to show you that, you know, what that unit is. So we get 3 times pi over 3. Those 3's cancel, and I just get pi inches. If you wanted to approximate that, you know, and write that as a decimal, you could. A lot of times, you know, if we can leave our answer exact without it being too messy, then we'll leave it exact. So, okie dokie. So that concludes section 7.1.